invitation. And I was asked to talk about the Wigner-function formalism and somehow the applications to the polarization business. And so I will, since the aim of this workshop is somehow to stay general as far as the organizers were pointing out, I will try to mostly to base on concepts. So, and trying to emphasize why we use the Wigner function formalism to study the dynamics of spin in heavy ion collisions, especially in heavy ion collisions. Okay, so first of all, one thing that I find very interesting about this business of polarization and in heavy ion collisions is that we can really establish a connection between a property which is inherently quantum, namely the spin of particles, and some feature of the macroscopic description of the QGP, which is basically classical, namely hydrodynamics. And this, I think, is also a very conceptual issue that I like to address, how this emergence of classical behavior comes from the quantum field theory, or in other words, what is left about quantum mechanics when we derive hydrodynamics. And so, well, this is just a very basic slide in which the spin is the most quantum feature, the first quantum feature one can think about. So it was first detected by the experiment by Stein and Gerlach. And of course, the non-relativistic spin operator, and so it has two states. So that's why we say it is sort of quantum. So two discrete states, spin up and spin down, for example. And the spin operator is given by the Pauli matrix, so the usual non-relativistic spin operator. And now, when we try to describe a system with many particles, which in addition have spin, the complexity, so the description becomes very difficult already. And there are many examples, and here what I would like to show is this famous Barnett effect in condensed matter. So no relativity so far, in principle. So we start to rotate a ferromagnet, and what we observe is that after some characteristic time, the ferromagnet gets magnetized along the rotation. And this already tells you that there is some connection between some macroscopic quantities, so namely the rotation of the ferromagnet, so the rotation, which is something that you can apply in the lab. You can experience this in a lab. So some rotation, some classical properties, some quantum property. So namely the fact that the spins of the constituents align along some direction. And so now the question we would like to ask is whether this kind of effects would emerge also in heavy ion collisions. So if there is something that resembles this in heavy ion collisions. And to do that, I briefly introduce what the physics of vorticity and spin, which anyways was already a bit discussed already. And so in the relativistic heavy ion collisions, we have the collision of two ions, and we undergo several steps, including some, and most importantly, we believe that a thermalized medium, namely the QGP, is formed after some time after the collision. And then it will eventually cools and will undergo some phase transition and eventually freezes out. So after which the particles, the hadrons, will free stream on our detectors, and this is what we detect. So the hadrons that are emitted by all this process. The very interesting feature of the QGP is that although it's a strongly interacting medium which obeys the laws of quantum chromodynamics, of course, this big complexity can be reduced actually when we describe the QGP, the quark-gluon plasma, in hydrodynamics. So the fluid can really well be described in terms of an effective theory, which is the relativistic hydrodynamics. And especially in central heavy ion collisions, we have in addition a large angular momentum, which at least in part can be transferred as as medium vorticity, which in turn, has already been shown, can lead to particle polarization along the vorticity. So this is basically a similar setup in this sense of we have a rotating medium and particle with spin, because QGP has quantum particles inside, quarks and gluons, and these particles will align along this direction of the vorticity, or the direction of the angular momentum. So of course the vorticity is a classical feature, as I was saying, of the medium. One can define the vorticity for also non-relativistic mediums, of course, non-relativistic fluids, and is basically the non-relativistic. The usual concept is the derivative of the fluid velocity. And there are some estimates in heavy ion about the behavior of the vorticity, and one can show, I mean, these calculations, these estimates show that the vorticity decreases in time, by the time is the time where the medium evolves. And also there is a feature which is maybe not so intuitive, that the strength of the vorticity also decreases as the center of mass energies of the colliding ions increases. And this is something, so we need to somehow find a good spot in the energy center of mass energy range, such that we can observe some effect related to vorticity. So the vorticity has to be high enough. And some estimates show that around this center of mass energy of 5 to 10 GeV, then we have that the vorticity can be actually very high, of the order of 10 to 21 seconds to the -1. And again, so as I said, so there is one can when there is a medium of quantum particles in a rotating system, there is a sort of an effective emergent interactions which couples this quantum and classical, and which couples the spin to the vorticity of the medium. And one can estimate some polarization due to vorticity by simply using a Boltzmann-like statistical factor, and in which the energy is effective energy, which takes into account interaction of spin and vorticity. And one can show that simply that the polarization is directed along the vorticity, and this is the factor. So we have an h bar and the Boltzmann constant over and the temperature in the denominator. And this is also what we expect to happen, roughly speaking, for the particles inside the medium. And this is what has been observed for the lambda baryons, and also actually for the vector mesons, but I will not touch this. This is also a problem that theory and experiments do not really agree. But anyways, we will focus on spin-half particles. So we will focus to the physics basically related to the lambda polarization. And this is something that has been observed, as said before, by the weak decay of the lambdas, which directly connects to the polarization vector of the lambdas. And it has been indeed shown that these estimates were consistent, and for the vorticity, and the vorticity is indeed very high. One of the is actually the highest fluid ever observed, and these are some order of magnitudes of highly rotating systems present in the universe. So we see that we are order of magnitudes far from any other system present in nature, observed so far. So the observable that was studied in heavy ion collisions was discussed very well in the previous talks, and I will not really talk about these new contributions now that has been found in by Francesco and other collaborators, and also the other group by Yin and the others. And what I would like to stress, though, that this theoretical developments and the polarization vectors, so this is basically the relativistic extension of the spin vector, is based on a few assumptions. So namely that the local equilibrium of spin degrees of freedom occurs, so it's reached. And also that the polarization of the hadrons determined at freeze out. So in this sense, I mean, there is no spin evolution during the medium. So spin doesn't behave as an independent dynamical variable, but it is always connected to the fluid properties, as this formula says, at the freeze out. So where the sigma is the integration over the freeze out surface. In this sense, we say that how we transfer the polarization from the fluid to the particles at freeze out, and then they will free stream to our detectors, and this is what we observe. So now the question, and there are many issues that have already been addressed about this longitudinal polarization and the possible explanations due to these new extra terms, or still people maybe not all agrees. And anyways, the question I would like to ask actually, which I think is very fundamental and which I'm very interested to address, is what happens if spin is included as a dynamical variable in this description. So hydrodynamics is a very good effective description, as we said. And then hydrodynamics, as we will see in a minute, can be derived from kinetic theory. And what happens if we include this spin as a dynamical variable? So the spin will really be an independent variable in principle and connected to fluid properties at some equilibrium stage. And this in principle is a question that I think one should address to understand better the dynamics of spin, which in principle is not really necessarily relevant only to heavy ions, but also other fields where relativistic quantum fluids are present. So this is our task. And so the starting point, since we are discussing purely quantum feature, the spin, the starting point is quantum field theory. So we would like to start from quantum field theory, but from a slightly different approach than what discussed before. Namely, we now want to formulate a kinetic theory. So we have a many particle system in which particles interact between each other, and they will somehow we assume that they can be described by sort of kinetic equations. So the point is that we want to formulate kinetic theory from quantum field theory. That's the point, and that's how the Wigner function will enter. So first of all, just to summarize our results that was been present in this paper, that was these papers, and the first one has been recently published. And so basically our theoretical frameworks will describe this orbital to spin angular momentum conversion necessarily for the spin to evolve and to align along the direction of vorticity. This will be this is driven by no local particle scatterings in a kinetic framework. This means that particles do not collide in one point, as this picture here illustrates, this cartoon, but rather there is some finite impact parameter between particles inside the medium. These are particles, the quarks that interact inside the medium, so to speak, and how they collide. So they collide with some finite impact parameter, which is, I think, a fairly reasonable assumption, because in principle the interactions are in general they have some range of interaction that don't necessarily collide at one point. Also, when we derive hydrodynamics from this kinetic theory, what this implies in our framework, is that the energy momentum tensor, which I will introduce later, which is the quantity which we use to describe hydrodynamics, will acquire an anti-symmetric part which will generate this spin evolution, the spin conversion. Anyways, this just to illustrate, but I will go through this now. First, to anticipate. First, then let's go to the kinetic theory, which is the main point of this talk. And first, let's discuss what we mean by classical kinetic theory, really generally, really briefly. So we have this system of particles, which in which we, of course, do not follow all the microscopic details, but what we say is that there is some distribution functions which tells us in average how these particles, where these particles are, and what their momentum is. So this sort of distribution function, what we call it. And what regulates the time evolution, the evolution of this distribution function is the Boltzmann equation, which tells you that the distribution function will change according to particle collisions. So this C is some collision kernel, collision term, which takes into account in which way particles collide. So this is basically the information that we need. We need distribution function and the microscopic interaction, so to speak. And then what do we mean that we derive hydrodynamics from kinetic theory? Well, as I will show later, so we are interested in the macroscopic quantities, energy and momentum, which are enclosed in the energy momentum tensor, which is this T. And these macroscopic quantities, which are related to fluid properties, are derived from the microscopic information of the distribution function by taking this proper average here, these proper moments of the distribution function. And this is basically, really roughly speaking, what we mean that we derive hydrodynamics from kinetic theory. So first we need to have a kinetic theory base, and then we get hydrodynamics. And now the question is how to formulate kinetic theory from quantum mechanics, right? This is the main question. We would like to keep as many quantum information as possible. And well, to do so, a possible way is to use the Wigner function. Here I first discuss here the Wigner function in quantum mechanics, which is don't need to go to quantum field theory in principle. So this is an object which can be defined in quantum mechanics, in ordinary quantum mechanics, and it's usually named as a quantum extension of the classical distribution function for the following reason. So we define the object here, the Wigner function, as this sort of Fourier transform, which is actually called Wild transform of the two wave functions here, where there is some interval, this y, this separation y. And this we obtain an object which has values on x and p. This is done for a pure state, but okay, can be generalized for a mixed state. But anyways, what we can immediately see is that this is an equivalent description of usual quantum mechanics and based on operators and wave functions, because it reduces to the usual probability density. And also the expectation values of any operator can be cast into this form, which really resembles some statistical average. So we have this W, which has values again in this phase space, and some function, which is some wild transform of the operator. So once we have the Wigner transform, then we have also the expectation value of any operator. And this establishes a connection between Schrödinger equation, so to speak, the ordinary quantum mechanics and the Wigner function. But the reason why we use this to discuss quantum kinetic theory is that the equations of motion for the Wigner function is a sort of Liouville or Boltzmann-like equation. And this is what is written here, this last equation here. And this really, using the Schrödinger equations, one can derive the equations of motion, which are the Boltzmann equation indeed. And this term C is something that depends on the potential of the Schrödinger equation. So which is how the particle interacts, right? So we have a very nice analogy with what I was showing before, that we have an evolution for this distribution function. which is driven by the interaction of our particles, our wave. And now the next step is to generalize this in quantum field theory, because we want to have proper description in relativistic quantum field theory. And what we do is very similar formally. It's inspired. I mean, we take the Wigner transform instead of the wave function. Here we have to deal with quantum fields. So we take the Wild transform of this 2-point function, where this psi here are the Dirac fields. And again,
can I quickly interrupt? We hear somebody vigorously typing in the background. If you could close your mic, please, so that we can listen to Enrico.
Really, me? Was it me? From me?
No, are you typing? No, I don't think you are typing.
No.
No, but somebody else is, and this is just a message to whoever is doing that.
Oh, okay. Oh, sorry. Okay. Okay, maybe I continue in case. Please let me know.
Yes, yeah, go ahead. Okay. We just had trouble hearing you because of the background noise.
Okay, sorry. Okay, okay. I hope most of it was hearable. Anyways, so again here we can, using the Dirac equation, we can derive the equations of motion for the Wigner function. And again, we have we can a complete analogy between the Dirac equation and the Wigner function equations of motion. And here we have these evolution equations here, where this right-hand side here is non-zero, only when interactions are present. So this row here is the interaction of our interacting Lagrangians, now cast into this form here. And by rearranging this, one can show that even for the quantum field theory Wigner function formulation, the Wigner function obeys a Boltzmann-like equation, where the C again has some information about the collisions. Now, the goal here, so this is why, again, we use Wigner function, and the goal here now is to solve it. So we need to find some strategy to solve this in presence of some interaction. And of course, a general solution of all this business, of these equations here is cannot be found in general for a general interaction term, because it's the same as finding a general solution for an interacting Dirac equation. In general, you cannot do it. And analytically, I mean, and the strategy is to see what happens around the classical value. So that's very important. So we perform an expansion in H bar. So we perform an expansion in terms of quantum levels and quantum corrections. Yeah. And we expand the Wigner function and also the collision term in terms of quantum corrections. And again, here there is these expansions will involve the local terms, so collisions which happens in one points, so to speak, and non-local terms. So this will be present both in this collision term, and in our scheme, the non-local collisions being driven by some gradients, because there is some finite impact parameter, then they would be only inside, they will only go with some H bar correction. So there will be some quantum feature in this sense. And here to a bit reshuffle the equations of motion, one can enlarge the phase space. It's just sort of a trick to ease the solution of the equations of motion, to include a classical variable, which is sort of which is related to spin. So this is this is just a classical trick. We don't with this exclude any quantum effects in particular. So this is just a convenient way of doing that. One can reduce the Boltzmann equation to a scalar Boltzmann equation, because here there are no Dirac indices anymore. This is contracted. And this is the advantage. So now we want to basically give an explicit form of this Boltzmann equation here. And And so that's basically the task. And yeah, so here I will not show any details of the calculation, just to say that the form of the collision term will be given by a sort of intuitive form, in the sense that this Gothic this curl W here is a term which includes the scattering amplitudes of the microscopic interaction, and this delta here will take into account about the displacement, the non-locality. And this is the form. So in the case of usual Boltzmann equation, the usual collision term, this delta is usually neglected. So that's the point. But here we can derive this form by a calculation, by a sort of long calculation. And so that's the form, and that's again the non-localities in this delta. So when we study equilibrium, so equilibrium in kinetic theory is defined as basically the form of the distribution function, which makes the collision term vanish. So that's the definition of equilibrium. And if it's global equilibrium, also the left-hand side of the Boltzmann equation will vanish. So in this sense, local equilibrium, when only the collision term vanishes, is not a solution of the Boltzmann equation. And here we just want to see whether the right-hand side here vanishes. And if we introduce an ansatz of for the distribution function, where here we take into account not only as conserve charges in the collisions, not only energy momentum, but also total angular momentum, which is taken into account by this term here, where sigma is this so-called spin potential, and this, sorry, omega, and sigma is a phase space spin dipole moment tensor. We see that if we plug that inside the collision term, one can show that indeed the collision that makes the right-hand side vanish, namely C vanish, are also the conditions which makes the left-hand side of the Boltzmann equation vanish. Namely, we obtain some conditions which are the global equilibrium conditions in this sense. And so if we start with the non-polarized medium, in this sense, if we put sigma, so we will say that sigma will relax to thermal vorticity, and this will be which is this gradients that was discussed already in the previous talks, and this will relax to thermal vorticity after in equilibrium. After some time, equilibration will occur. And so in this sense, we have this kinetic picture of polarization through rotations. So now just a couple of slides on how we derive hydrodynamics. So first of all, hydrodynamics is the conservation of energy and momentum usually. That's the conventional hydrodynamics. And the object is this energy momentum tensor that I introduced before, which basically tells us that the quantities that we are interested in, the macroscopic quantities, will be the energy density, the energy flux, the shear, and all these ideal and derivative quantities, which are all encoded in the energy momentum tensor. And the equations of motion are the one from conservation energy and momentum, which is given by this. So now, if we have spin and we start from quantum field theory, what we need to, what is natural to assume is also that the conservation of total angular momentum also has to be satisfied, so has to be taken into account. And this is from the Noether's theorem. What one normally does is consider the canonical energy momentum tensor, which is the one that one can derive from the invariance of the space-time translation and the rotations of our microscopic theory, which can be, for example, the Dirac theory in our case. And we have that if that in general, so the total current, which is associated to the total angular momentum, is given by an orbital is given by this J, which is the total angular momentum tensor. which is in general given by an orbital-like component here, expressed with the energy momentum tensor, and a spin component, which is expressed with this S here, this green S here, which is the so-called spin tensor. And this is the point, the new dynamical variables, so to speak, that we introduce in hydrodynamics, in spin hydrodynamics. And in general, the spin tensor is not conserved, but is given, so the source of the for the change of spin tensor is given by the antisymmetric part of the energy momentum tensor here. So here I will not talk much about this. I will refer to Nora Weigenand's talk on Monday. But this energy momentum and spin tensor will be, it suffers from some ambiguity in the definition. These are called pseudo-gauge transformations. So we can reshuffle these densities such that the total charges are left invariant, for example. And but okay, this is, I will not really focus on that. Just here to say that there is this ambiguity, and one has to somehow make a choice of this pseudo gauge, of this pseudo gauge. And anyways, once we establish this, what we mean by spin hydrodynamics is that instead only of energy momentum conservation here, we also include as a dynamical variable the conservation of total angular momentum, or the non-conservation of the spin tensor, which are the same thing. And the unknowns are the beta fields and this new spin potential. And again, what I said is not uniquely defined. And in our work, we use a specific choice for the energy momentum tensor, spin tensor, which are this Ilgenwald and Voigt-Thyssen, because the canonical spin tensor is indeed not a real tensor in the sense of Lorentz tensor for the thanks. I saw the 5 minutes for the it's not a real tensor in the meaning of the Lorentz transformations. So for free fields, so we there is this solution proposed by these two Dutch guys here. And here, once we choose the pseudo gauge, there is actually a nice connection between kinetic theory and hydrodynamics. So namely, the conservation of energy momentum is given by this integral involving the collisions, and we see that if the the momentum is the collision invariant like it should, then this is 0, and that's all right. Or now, the new thing is that in this framework, the non-conservation of the spin tensor is given by this collision term times this dipole moment tensor here. This will describe some spin dynamics in the collision, right? So now in non-local collisions, this dipole moment tensor is not conserved. This means that the antisymmetric parts will be different from 0, the energy momentum tensor. This is the antisymmetric part. And this means that if there is such non-locality of the collisions in this framework, we do not have a conversion, sorry, we do have some sort of evolution of the spin tensor. And in this sense, we say that there is conversion between the spin and the angular momentum of the fluid, if the spin tensor can be somehow reduced to, can be thought as an angular momentum, spin density of the fluid. Also, if the energy momentum tensor is symmetric, so this antisymmetric part is 0, which happens for local collisions, then spin is a collisional invariance, because in local collision, spin is a collisional invariance. And also, as we discussed in global equilibrium, trivially, because the collision term is 0. So this is also happens to be conserve the spin tensor in global equilibrium. So if we are discussing a sort of new variable which around equilibrium is in global equilibrium is exactly conserved. So in this sense, it's a good hydrodynamic variable. But as soon as we deviate from global equilibrium, it starts to have some non-conservation. And in this sense, also in this way, this form of the HW pseudo gauge seems to be suitable for this description of spin fluids. Also, if we have no local collisions in general, we have dissipative dynamics, and in this sense, we have fluids that gets polarized through rotation. So now the problem is what happened, why we need to introduce local collision, we need to introduce dissipative dynamics. Well, here I just give an intuitive argument based on scales. So usually hydrodynamics is based on the separation of scales between some mean free path, which is this MFP, and mean free path, which has to be much smaller than the scale over which hydrodynamic quantities like velocity, temperature vary. So this is also a measure of the deviations from equilibrium, from local equilibrium indeed. So namely, usually unusual relativity, unusual hydrodynamics, and this called Knudsen number, and the dissipative effects will be on the order of this Knudsen number in general. So now we have a new scale in the game which is associated to spin effects and non-locality, and this scale can be, which is a purely quantum, related to a purely quantum effects, and we define it as this non-locality scale over the hydro scale. And if this delta is comparable to the mean free path, then there is no reason to include spin effects and exclude dissipation effects. So in this sense, we intuitively say that when we have this spin non-locality scales, because in our framework non-locality and spin effects are on the same H bar, then we have that the usual local equilibrium definition of usual hydrodynamics somehow has to be revised according to our framework. Well, here now, just as an outlook, what we want to do with this machinery is to calculate the deviations from the usual formulas from of the polarization vectors to find effects in case in observables in heavy ion collisions, and that's what the future work would lead us to. Okay, so that's basically it. I discussed that vorticity and spin are inherently connected, and also that spin degrees of freedom must be taken into account. I mean, it's a natural extension of all this business in to take into account spin as a dynamical variable, and also that in general, we suggest that the presence of non-local collisions will lead to dissipative effects. And also, as I showed, that somehow spin brings conceptual issues in the emergence of hydrodynamics. Okay, that was that was it. Thank you.
And thank you for a nice talk. So let's go ahead with questions. Francesco.
Yeah, I mean, yes, thank you for
Hi, Francesco.
Really, ciao. I have not really got the point, maybe because I got distracted while about the fact that, I mean, one of your conclusions, a quantum field theory calculation suggests that spin hydrodynamics is only dissipative in the presence of non-local particle collisions. So therefore, I mean, actually that in the slide number 30, you said that, yes, this one, that spin effects no standard notion of local equilibrium. So can you really, I mean, I didn't get it.
So the thing is that in our framework, the spin effects, including the non-locality, are treated as H-bar order, okay? This is when we perform the H-bar expansion, this is what we do. And this means that if we introduce a new scale associated to this, when we derive when we compare this microscopic scale to a macroscopic scale to discuss hydrodynamics, this kappa here, this is the new sort of Knudsen number, but with delta being this new spin scale. When we compare it to the hydro scale, we have that this is what the correction, the quantum correction should go, right? So if this new delta is comparable, let's say, with the mean free path, so surely it's not bigger, I mean, but it's a little smaller or similar, in order anyways to have some sort of probably molecular chaos or something similar that we still want to respect, then you can immediately say that you can immediately see that this kappa and Knudsen here, the usual Knudsen number, are related by a ratio of delta over mean free path. And this means that if delta is more or less the same as the mean free path, then also this relation between the Knudsen usual and the quantum one holds. This in turn means that if you include the kappa here, because we want to include spin effects, and this is the same order of the, more or less, of the usual Knudsen, then we are not really legitimate to exclude one and include the other in this sense. In this sense, but this is all holds because of our power count. Right? Okay.
So I think I have to digest a little. I mean, to digest this because I really don't. I don't get the. So maybe I have to study your assessment more in detail. However, but does this is this an argument which is related to a kinetic approach? Because you know that in quantum field theory, then in this the approach that I talked about, yes. The definition of local thermodynamic equilibrium is independent of the of there is an underlying kinetic say theory or not. So in other words, it's purely quantum field theory say related, and therefore I was wondering whether this is an argument which say somehow depends on a kinetic picture or it is more general.
Well, here, well, it depends on a kinetic picture in the sense that you need to have some separation of scales. I mean, so here we derive some macroscopic quantities from some microscopic quantities, and in this sense, we need to have some, in order for hydrodynamics to make sense, we need some separation of scale in this sense. But this delta here is a scale that it should also be somehow present in the Zubarev somehow, because if you consider, so if you expand in terms of gradients of velocities,
maybe we can discuss this later.
Yeah, we can discuss in the Q&A.
Other people in the
yeah, that's true.
Yeah, thanks. So Giorgio.
Thanks. Well, this is a follow-up. This is a follow-up comment. This is a beautiful result, which you can see in many different ways. It's certainly more general.
Yeah, you also worked on this. Yes.
Yeah, it's even in equilibrium, polarization makes sound waves and vortices mix, and if you calculate the mixing in general, the propagation speed of a sound wave becomes a quartic, which will have solutions which break the speed of light. The general sort of the qualitative way to see this, which is consistent actually with Francesco's earlier talk, is that if you have a gradient in flow, just from the fact that you have a quantum nature, you have a wave function, this gradient of the flow will be transferred to spin. And the transfer of gradient to microscopic degrees of freedom by definition is dissipation. So this is a very general principle is emerging that spin orbit interactions, which are defined at equilibrium, spin susceptibility is connected to a fluctuation dissipation relation that gives you a minimum amount of dissipation, which is kind of independent of ADS, CFT, or anything else. Spin implies viscosity. Spin implies relaxation, and this is one way of showing it. But this is sort of very nice in general.
I think I agree. Yes. Thank you.
Okay, so the last question from Lorenzo. Please go ahead.
Yes. Hello.
Yes,
hello.
I hear you.
Thank you for the nice talk. I just wanted to know, generalizing all this picture to general relativity. Well, you know, you like more having the symmetric stress energy tensor, that is the Wigner-function Rosenfeld. Do you think the formalism would become very complicated? I guess you would need to introduce a tetrad so to work. Do you think that going to general relativity would be too much complicated, or that okay, we do it and it's not a big deal?
No, I think no. Well, for sure, it's much more complicated. But the concept, I think, is what you say, that in order to introduce the spin tensor, one has to introduce the tetrad, and also in general relativity, in general, you don't need to have a symmetric energy momentum tensor. In principle, you don't have to, in the sense that there are all these series of works by people that want to somehow find the gauge theory for gravity, and for them it's more natural to introduce actually a spin tensor, which is defined as the derivative of the action with respect to the torsion, to some torsion.
Okay, yeah, I see.
In this sense, when we have spin degrees of freedom, also classical, because we can also talk about classical, right, sort of Dirac equation in this sense, not quantized. You need to have some information that tells you more and about how the spin behaves, and the Wigner-function may not be the only one. I mean, actually, it has been argued that that may not be actually the best one for this kind of thing. But yeah, in principle, I think one can extend this to GR, yes, with its proper care.
Okay, but, thank you.
Sure.
Okay, and thanks again for a nice talk in the discussion.
Yeah.
I do not know, actually, since we had some interrupted discussion after Francesco's talk, maybe we use those 8 minutes to resume it before the next session starts. I don't know.
Yeah.